Okay, so this will be on infinite sequences, series, and I'm going to add one thing to the title, limits. Okay. Okay, so it's infinite sequences, series, and limits. First, we're going to look at some different sequences and look at what they're approaching. Okay? What is this sequence approaching? Say I give you the sequence 1/1/2, 1/4, 1/8, 1/16. What is that sequence getting closer and closer to? What's that? No. What's it getting closer to? 0. It's getting closer and closer to 0. Will this ever reach 0? No. But it's getting closer and closer. What that looks like in terms of limits, it's getting closer and closer to 0 as a limit, but it won't ever reach it. The author's going to introduce the limit notation, and you can write this sequence. You're actually multiplying by 2 in the denominator each time. So if we write it 1/2 to the n power as n approaches infinity. Okay? So if you substituted in, if n was 1, you'd have 1/2. If n was 2, you'd have 1/4. If n was 3, you'd have 1/8, 1/16, and so on. But that denominator is never, and the fraction itself is never going to go to 0. It will approach it as a limit. So the limit is 0. Okay? And this is some new notation for you that you'll use in here and you'll use in Calc. Okay? Look at another. What is this one approaching? Same directions. 1/1, 1/2, 1/3, 1/4, 1/5. What's it getting closer and closer to? 0. But it won't ever reach 0. Okay? You can write this one as the limit of 1/n as n, and that's a little arrow to the right, as n approaches, and that's the infinity symbol. So when you start substituting in, you always start with 1. So you put 1/1, 1/2, 1/3, and it's approaching 0 as a limit. Okay? Okay, now we're going to talk some more about limits. Now the author is going to give you the limit of 3n plus 1 up in the numerator all over n as n approaches infinity. This top part is a polynomial. Put a little abbreviation there. Polynomial because it has more than one term added or subtracted together. And this bottom part is a monomial. If it's a polynomial over a monomial, you can split it up. Okay? So it's okay to write it. You still need an equal sign and then the limit notation. A lot of people get confused and think the equal sign goes in between the limit and the problem. No. It's the limit as n approaches infinity. Then you can split that up. 3n over n plus 1 over n. If it's a polynomial, you can split it up. Okay? Then reduce it. Okay, if you reduce the n's would divide out. Okay, and then it would be the limit as n goes to infinity of 3 plus 1 over n. Now, when you take the limit of each part separately, that's when this limit notation disappears. Okay? So you're going to have an equal sign. Now, you take the limit of each part separately. So you look at what's the limit of 3. Well, you have to look at that sequence. If you had the sequence 3, 3, 3, 3, 3, what's it approaching? 3. If you look at this part, 1 over n, what's it approaching? 0. So 3 plus 0 is 3. Okay? And you can actually figure that if you would go back to this original problem and say, everywhere you see an n, substitute in a 1. Then substitute in a 2. Substitute in a 3. And you will get a sequence that will approach 3 as the limit. Okay, it doesn't hit 3, it just approaches that as the limit. Okay, that's a polynomial over a monomial. Okay, now let's do a polynomial over a polynomial. Say you have the limit of 4n squared plus n over 2n squared plus 1 as n approaches infinity. Okay, so on this one, we've got a polynomial over a polynomial. It's got plus or minus signs in between, so it's polynomial over a polynomial. Okay, what you do on this one is you look at all the terms and find the term with the highest degree. Well, in this case, the highest degree is an n squared. Okay? You divide every term of your polynomial, top and bottom, by that highest degree. Okay, so you'd have the limit of 4n squared over n squared plus n over n squared, and it's all over 2n squared over n squared plus 1 over n squared. And I'm going to move this down a little bit so it's a little bit better. As n goes to infinity. So you take, on a polynomial, you take each term, divide by the highest degree. Notice I did not divide by the 2 in front. Okay? Now reduce it. Okay? If you reduce it, these n squareds divide out. Okay? So I still have the limit of 4 plus. When you reduce this, what are you going to get? 1 over n. Okay? And if these n squareds divide out, you just have 2 and 1 over n squared as n goes to infinity. Now you take the limit of each part separately. When you do that, this limit notation disappears. You don't write that down. So you say, what's the limit of 4? Well, that's the sequence 4, 4, 4. It's just approaching 4. The limit of 1 over n, that went to 0, right? From up above. Sequence 2, 2, 2, that just approaches 2. Plus 1 over n squared. Ooh, we haven't done that one. So 1 over n squared. If you substituted in 1, it'd be 1 over 1 squared, which would be 1. 1 over 2 squared would be 1/4. 1 over 3 squared would be 1/9. 1/16. What's it getting closer to? 0. So that's also approaching 0. So 4 divided by 2 is 2. The limit of that is 2. Okay? Okay? Okay. Each one of those is approaching a specific number. Okay? Any questions on that one? Mm-hmm. Oh, I'm subtracting the exponents. Remember, if you had an n to the first and an n squared, you can write it out the long way, and then these would reduce. You'd still have a 1 down at the bottom. Okay. Or, no, that's fine. If you had something like this, say I had an n to the third over an n to the seventh, you'd subtract the exponents, I'd have 1 over n to the fourth. Or I could end up with an n to the -4 power. Okay. If you want to work with positive exponents, if the larger exponent's in the bottom, then that part of your answer is in the bottom. So if you had n to the 7th over n to the 3rd, if I turn it around, that would be n to the 4th up on top. Okay. This one's the same as n to the -4. Okay. Okay.
Oh.
Okay. Okay, let's keep going. Another example. Say if I had the limit of negative 1, put that in parentheses, negative 1 to the n power as n approaches infinity. Okay, so you need to look at this sequence. Negative 1 to the first, negative 1 to the second, negative 1 to the third, negative 1 to the fourth, negative 1 to the fifth, dot, dot, dot. Okay, negative 1 to the first would be negative 1. Negative 1 squared, 1. Negative 1 to the third. Yep. And it's just gonna oscillate back and forth. Whoops. It's just gonna oscillate back and forth, right? So is that approaching anything? It's going negative 1, 1, negative 1, 1. On your graph, that's what it's going to do. It's just going to bounce back and forth on the y values from negative 1 to 1. Okay? So this one is no limit exists or no limit. Some authors will just say no limit exists. Okay? Okay. Now, in years past, I've always just taught these two and let you work it. That's a lot of work. Okay? Mathematicians are lazy. There has got to be a shortcut. Okay? Here's the calc shortcut. Okay? So anybody that goes into calc next year, you already know the shortcut. Okay? And that's what I will call it. And you can use, on the homework, you can use the calc shortcut. So start this. Okay? If it's a rational function for a rational function. And the reason I teach the other method is because some calc professors at the universities don't want you to know the shortcut yet. Okay? So, but you could check it by the shortcut anyway. For a rational function, f of x, if you have a function on top, p of x divided by h of x. Okay? Okay, number one. If the degree of p of x is less than the degree of h of x, then the limit of f of x as x approaches, and it'll say positive or negative infinity. As x goes out to infinity, as x gets large, the limit is 0. If the degree is less on top. Okay, so on this one, if the degree is less on top than the degree on the bottom, okay, then the limit is 0. Okay? And you just do it by sight. Okay? Okay, the second one. If the degree, and you can abbreviate it, degree of p of x equals the degree of h of x, if their degrees are the same, and you're looking at their exponents when you're talking the degrees, okay, then the limit of f of x as x approaches positive or negative infinity, okay, equals some constant. They're using k for the constant. A constant's just a number, okay, where k is the ratio of the leading coefficients. Okay, and then the third one, if the degree of p of x is greater than the degree of h of x, then the limit, of f of x as x approaches positive or negative infinity, okay, is positive or negative infinity. And you can actually tell on the graph if it's going up, positive infinity, if it's going down, negative infinity. So if the degree is larger on top, okay, then it's going to be infinity. Okay. Okay. Now, if you go back up, we're going to look at like the ones we did here and another example. Okay. So they will say in the book, find the limit. You could work it the long way that I showed you up above, but here's using the calc shortcut. Okay. Okay, if we said find the limit, up in the numerator put 3n squared plus 2, okay, and it's all over n as n goes to positive or negative infinity. Okay, so you look at the degrees. The degree of the numerator, the highest term, is 2. The degree of the denominator, that exponent's understood to be a 1. The degree is larger on top, okay, that would be this number 3. If the degree of p of x is greater than the degree of h of x, okay, then it's infinity, positive or negative infinity. Now, you need to decide which one is it, okay? So, let's graph it on the calculator. When you put that in on the calculator, you just have to change the n's to x. And you need to know to put parentheses around. Okay, so we'd have parentheses 3x squared plus 2, and then divide by x. Okay, and just do zoom 6 to start, zoom standard. Okay, and you actually end up with a graph. There would actually be an asymptote, a horizontal or a diagonal asymptote, and the graph would look something like this. Okay. So as x is going to positive or negative infinity, your graph is going to positive or negative infinity. Okay. As x is getting large, this one's going to positive infinity. As x is getting small to negative infinity, y is going to negative infinity. So positive or negative infinity. Okay. Okay. Look at another example. Say I give you the limit up in the numerator, 5x squared plus 3x minus 1, and it's all over x cubed plus 2 as x goes to positive or negative infinity. And the shortcut only works when this is going to infinity. Next year we're going to go to a specific number, and that shortcut doesn't work on that. Okay? So you look at the degrees. The degree is less on top. So you go back up to your calc shortcut. If the degree of the numerator is less than the degree of the denominator, the limit is 0. Okay? So we know by sight, without doing all that work, the shortcut is the limit is 0. Okay, now let's graph that one. Okay? Just clear out that other one. Put in 5x squared plus 3x minus 1 divided by, and then the quantity x cubed plus 2. And just do zoom 6 is okay. This, on my calculator, it actually shows an asymptote. This is not part of the graph. You should know if you have an 83 or an 83 plus that is a dashed line. Anytime you see those spikes, then you know that's a dashed line. Most of the time, no, not on the vertical ones. Okay, so you would have and this is pretty quick. I'd take more time if I was doing this for, okay. We're going to have something like this. It's going to cross, goes up, and then it approaches. Okay. So in both cases, what's this graph approaching? As x goes to infinity, what's y going to? Getting closer and closer to 0, isn't it? As x goes to negative infinity, what's y going to? Getting closer and closer to that 0. Okay. The limit's always red on the y-axis. It's getting closer and closer to 0. Okay. 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 If we went back up here to our original problems, go back up to 3 and 4. Degree of this one would be 1. Degree of this one would be 1. If they are the same, it's the ratio of the leading coefficients, which would be 3. A lot quicker than doing all that work. The degree of this one is 2. Degree of this one is 2. Degrees are the same. It's the ratio of the leading coefficients. 2. A lot quicker. Calc shortcut. Okay. I think you'll like the calc shortcut. If the degrees are the same, it's the ratio of the leading coefficients. Yep. Divide them out. Okay. So if I gave you one like this, should be able to do it by sight. If I said up in the numerator is 5x squared plus 8x, down in the denominator is 6x squared minus 9, as x goes to positive or negative infinity. By sight, what's the, it's the ratio of the leading coefficients, 5, 6. Okay, because those degrees are the same. The highest degrees are the same. It's the ratio of the leading coefficients. Okay, and I always tell people, if you forget on the other two, let's say I did the limit of 5x to the third minus 8x over x plus 2 as x goes to infinity, positive or negative infinity. Okay, if you forget, is this infinity or is this 0? It's one or the other. Okay. If you forget, here's what I do. I pull out just the x cubed over x and go back to what you did in Algebra 2. If you reduce that, what are you going to get? X squared. Now, start substituting in. If x is 1, 1 squared is 1. If x is 2, 2 squared is 4. If x is 3, 3 squared is 9. What's this going to? Is it going to 0 or is it going to infinity? It's going to infinity. That's the easiest way. If you forget, is it infinity or is it 0? Pull out just that part of the problem. Okay? You have to figure out, well, it will always say x is going to positive or negative infinity. If you forget if this answer is infinity or is this answer 0. Which one is it? So you want to pull out just that part, work just that much, and you see it's getting larger and larger. Okay. Plus you could also graph it. Okay. If I didn't give you the calculator though, that's the easiest way. So if I said, let's turn this around. Let's put the x minus 4 on top over 6x to the second plus 3x minus 9. As x goes to positive or negative infinity. Same thing. Let's say you get to the test. You cannot remember, is this 0 or is this infinity? Okay. You look at this, just pull out just that much. Take the x over the x squared. And this is like x to the first. If you reduce that, what's left? 1 over x. Now you always start substituting in 1. So if x is 1, you'd have 1. If x is 2, you'd have 1/2. If x is 3, you'd have 1/3, 1/4. Okay, getting smaller and smaller. That one's approaching 0. Okay, so that's the easiest way to remember that. Okay. Okay.